Hi, today I'll be speaking about cortical computation via iterative constructions, and this is joint work with my advisor, Santosh Vempala at Georgia Tech and Christos Papadimitriou at Berkeley. So, our high-level goal is to develop a mathematical framework to explain cognitive function, but today, more specifically, I'll be giving a neurally plausible algorithm for computing a threshold function. So to start, I'll give a basic definition of neural plausibility and describe our motivation in a little bit more detail. So the brain is made of approximately 80 billion neurons, each of which is connected via synapses to between 1,000 and 10,000 other neurons. And the brain is roughly constant in the distribution and types of neurons. Therefore, if an algorithm is neurally plausible, it must be highly distributed, require little synchrony, and little global control. So we'll be working in a very basic framework, and it just requires a couple of definitions. First, we say that an item is a collection of neurons representing a concept or an object. So the item will fire if we recognize the object or concept. So this can be something concrete, like a place like Central Park, or something more abstract, like our notion of mathematics. And we're allowed two operations on items. We can take the AND of two items, or the OR of two items. And we say that building a small tree of ANDs and ORs is neurally plausible. So in this example, this AND item is going to fire if items A or B and item C or D will fire. So our motivation is this. Given this really basic framework, what can we accomplish? So using only ANDs and ORs, what functions can we build in a neurally plausible way? How might these functions be employed in cognition? And finally, how are such functions learned? So today, as I mentioned before, I'll be focusing on threshold functions, and I'll hopefully begin to answer some of these questions. So just to make sure we're all on the same page, function f is a t threshold function if it evaluates to 1 for inputs above t and evaluates to 0 for inputs below t. Here's a half threshold function. There's half. So why are we focusing on thresholds? First, we imagine that thresholds are fundamental in neuroscience, much like they are in computer science. So an example we imagine is object recognition. So we're all able to identify this as an elephant, and there are many features that we might associate with an elephant. In this picture, we only see some subset of these features, but we're able to identify the picture as an elephant. So maybe there's some sort of threshold function on what we see that allows us to determine that this is an elephant. And of course, we have mathematical inspiration from the works of Moore, Shannon, and Valiant, and in a few slides, I'll be more specific about their contributions. So in this next section, I'm going to give you a construction of a threshold function in a neurally plausible way. And the structure we build, we just call an iterative construction or an iterative tree. So here's how it works. The input to the algorithm is a vector of length n. We can think of these as features and feature items and a probability distribution on a set of small trees. And the goal of the algorithm is to create an item that's going to fire if and only if less or more than t fraction of the inputs are firing. So if we want to go back to the elephant example, you can think of the inputs as the features we see, the items we see, and our goal is to essentially create an item that represents the elephant. So here's how it works. First, we pick a tree according to the probability distribution. Say this tree is chosen. Then we're going to pick 3 input items at random, uniformly at random, and then build the tree on those items. We're going to do the same thing. Say this tree is chosen. Again, choose 3 inputs, build the tree. We're going to repeat this and create an entire level of items in this way. Now we iterate. We pick a tree again. This time, instead of choosing these items to be leaves, we're going to choose from these items uniformly at random to be leaves. Build the tree. We repeat. We have another level. And we keep doing this. And now I claim that items at this high level are going to fire if and only if t fraction of these inputs fire. And by if and only if, I mean if and only if with high probability. Okay, so our theorem is as follows. If we take this construction for any t, with this tree with probability t, this tree with probability t, then items at this level, log 1 over delta plus log n, are going to be accurately compute the threshold function with probability at least 1 minus delta. And we call this rate of convergence linear convergence. The n is just the number of inputs. So natural question is, what about faster convergence? So here we can get quadratic convergence, which would be log 1 over delta instead of log 1 over delta. And this is ideal if you want to be accurate on all 2 to the n inputs. So we're able to show that you can also achieve arbitrary thresholds with this faster convergence behavior. However, the size of our building block trees will need to grow in order to achieve thresholds near the boundary. And so this is about 1 over root n is how big the trees have to be to achieve these really small thresholds. So now's a good time to pause and compare to previous work. So motivated by the design of stable circuits, Moore and Shannon studied recursive processes of and/or circuits in the 50s. Independently, in the 80s, Valiant showed that if we take our construction with choosing this tree every time, we get convergence to a 0.38 threshold function quadratically. So our work differs in 2 key ways. The first is that previously these constructions were thought of purely in a recursive manner, whereas we're imagining them being built bottom up. Therefore, we provide an analysis of how wide the levels need to be in order to ensure high accuracy, which isn't something I'm going to speak about today, but is in our paper. And the second key difference is that they restricted themselves to 1 building block tree or circuit at a time, and we're allowing probability distributions over circuits, or over trees. So this allows us more functions with smaller building blocks. So now I'm going to quickly give you 2 alternate constructions that also converge to threshold functions, but don't require creating levels. So that in the exponential iterative construction, the probability an item participates in future item creation decays exponentially with time. So it's going to look a little something like this. As we build up, we don't have levels anymore. We just sample from previous items, with more previous items being more likely. Okay. And we also have the wild construction, which is the exponential construction with no decay. So each item is equally likely to be chosen at any point. And so both of these constructions also converge to threshold functions, but they are more neurally plausible because there's less coordination required. Finally, for the last couple minutes, I'm going to go into questions about learning thresholds. So previously, I showed if you gave me an n and a threshold t, I could construct an iterative tree such that the high-level item is going to create that t or is going to represent that t threshold function. But now, what if instead you just give me a set of labeled examples that are coming from a threshold function, but you don't tell me what t is? Can I still create this tree? So if we were able to do that, we'd want to do that in a neurally plausible way. So quickly go over some ideal features for neurally plausible learning. First, again, highly distributed, little synchrony, and little global control. Second, we only want to access information about items that are currently firing. Third, we want our learning to somehow be able to build on existing knowledge. And this is where we really believe that our representations of iterative trees are key because of their hierarchical structure. And finally, we want learning to be possible from relatively few examples and non-examples, because as people, we're able to learn this way. So our result so far on the learning front is that we have a very simple one-shot learning algorithm for thresholds. We really believe that this is the tip of the iceberg. There's lots of learning questions we can ask. For example, given a set of examples where only some features are relevant, can we identify which features are relevant and learn a threshold function on them? More generally, can we construct and learn general linear weighted threshold functions or even non-linear threshold functions? To do this, somehow we'd have to break the symmetry of our design. And finally, in the most general setting, given a set of inputs and a set of outputs, can we learn the distribution on building block trees that would produce the corresponding outputs? Thank you.